Imagine a river so immense, so alive, that it constantly reinvents itself.
Mm,
Not in, dramatic floods or sudden shifts, but more like a rhythmic, pulsing dance.
that's a great way to put it.
We're going to plunge into this vast, living system that shapes and reshapes itself in truly surprising ways. We're taking you on a deep dive today, right into the heart of the Amazon River.
Welcome to the deep dive. Yeah, today we're unpacking the morphodynamics, how the shape changes of the Peruvian Amazon River's really fascinating anabranching structure.
Anabranching structures.
We've been digging into a very detailed research article, Abad and others from 2024. And what's cool is that it combines 35 years of satellite observations with direct, on-the-ground field measurements.
Wow, 35 years.
Yeah, it gives us this incredible understanding of how this massive river system actually builds and maintains itself.
And by the end of this deep dive, you'll have, I think, a completely new perspective on how these huge mega rivers operate. We'll discover what anabranching rivers truly are, how they manage to achieve this unique kind of equilibrium, this balance, without the typical meander cutoffs you might expect.
Right, none of those dramatic shortcuts.
We'll look at the subtle but really powerful influence of tributaries joining the main river, and why understanding all this dynamism is absolutely crucial for the future of this vital ecosystem.
It's not just geography, is it?
No, it's really about getting a feel for the very pulse of one of Earth's most important rivers.
So let's start maybe by decoding that term, anabranching. What are we actually talking about?
Good idea.
When we talk about these rivers, we mean multi-channel systems. They're distinct from, say, braided rivers or anastomosing types.
Okay.
Their key characteristic is that they split the flow. It divides into multiple channels, which is actually maybe surprisingly very efficient for maximizing sediment transport, especially in these really low gradient regions.
And that low gradient point is key for the Amazon, isn't it? Because it has this remarkably low slope. I mean, almost flat, right? Something like 10 to the -5 near Iquitos.
Exactly. Incredibly gentle slope. Yet, despite that, the Peruvian Amazon is an absolute powerhouse.
Yeah.
It carries this immense average annual water discharge, 34,000 cubic meters per second,
34,000.
and an astonishing sediment yield, 541 million tons per year. Just think about that amount of material moving.
It's hard to even picture. So what makes this anabranching pattern so dominant in rivers of this scale, these mega rivers, as the researchers call them?
That's precisely it. Anabranching patterns are really typical in these mega rivers, the ones with average annual discharges over, say, 17,000 cubic meters per second.
So the Amazon is well over that threshold.
Way over. And that low slope is exactly why the anabranching system becomes so critical. It helps move all that water and, crucially, all that sediment efficiently.
Okay, makes sense.
The study we're diving into focuses on a specific stretch, 650 kilometers of the Peruvian Amazon.
Where exactly?
It starts right at the confluence where the Marañón and Ucayali rivers join to actually form the Amazon, and it goes all the way to the Peru-Brazil-Colombia border.
Got it.
And within just that region, they identified 21 distinct anabranching structures, mostly formed within alluvial deposits, basically. The loose sand, silt, and clay the river itself has laid down over time.
Okay, so 21 structures over 650 kilometers. And the study covers 35 years. How on earth did the researchers track the Amazon's pulse, its changes, over such a long time? What tools did they use?
Well, that's where remote sensing, specifically Landsat satellite imagery, became absolutely essential.
Right, the eye in the sky.
Exactly. They meticulously analyzed data every 5 years, and always during the dry season.
Why the dry season?
To get a consistent, clearer picture of the river's actual shape, its plan form, without the complications of high water levels. They did this from 1985 right up to 2020.
That longitudinal view, that long-term perspective, must be key for understanding these slow dynamic processes.
Absolutely crucial. You wouldn't see these patterns otherwise.
So they had decades of satellite pictures. How do they turn those pixels into real understanding, into river geometry and behavior?
It was a pretty painstaking process, I imagine. From those pixels, they extracted really precise patterns, defining the center lines of the channels, mapping all the islands.
There must be a lot of islands.
Oh, yeah. And identifying where the flow splits, those are the bifurcation points, and where it comes back together, the confluence points.
Bifurcation and confluence. Got it.
And what's really interesting is they even distinguish between single structures, which are generally stable, and compound ones, which tend to be more unstable.
Okay, stable versus unstable.
Which then allowed them to define 27 substructures for even more detailed, focused analysis.
And measuring the river's activity, you mentioned that earlier.
Yeah.
How did they quantify something as complex as erosion and deposition over that huge area in time?
They came up with some clever metrics. They basically categorized areas that changed from land to water over time as erosion,
Makes sense.
and areas that went from water to land as deposition. Then they quantified this as activity, an annual percentage change in area. It's a neat way to highlight those subtle, continuous shifts that you wouldn't just see by looking.
That is clever. And it wasn't just satellite data, was it? There was field work, too.
Correct. Beyond the satellite view, they also went out there with acoustic Doppler current profilers, or ADCP instruments.
What do those do?
They measure water velocity across a channel, so they could characterize the flow structure, the water fluxes directly within the river. It adds another layer, the hydrodynamics on the ground, to complement the remote sensing.
Okay, so we have this picture of how they studied it. Now let's talk about the static story first. What the numbers tell us about the river's basic shape and size. What did they find about the different channels?
Well, looking at the channels themselves, there's a clear difference. The
Right.
main channels and the free channels, those are the stretches without any islands in them. They're significantly wider. We're talking an average of around 1,500 meters.
1,500 meters wide, almost a mile.
Yeah, huge. In contrast, the secondary channels, the ones splitting off around islands, they're much narrower, averaging only about 346 meters.
So roughly a third of the width, maybe less.
Exactly. It shows this real hierarchy in the river's architecture. You have these vast main conduits and then these smaller secondary pathways.
What about how curvy they are? The sinuosity.
The free channels without islands are actually the straightest. Sinuosity around 1.05, which is pretty straight for a river.
Very straight.
The main and secondary channels have slightly higher sinuosities. But here's a fascinating point. Even though secondary channels can become more active, more change happens there when the main channel gets quite sinuous. The secondary channels themselves are considered non-mature. They don't seem to develop those really deep, pronounced curves, those high sinuosities that would typically lead to meander cutoffs in other river types.
So they don't pinch themselves off like a classic meandering river. They maintain a different kind of stability.
Precisely. They behave differently.
And in terms of their length, the wavelength of their bends.
Big difference there, too. The main channels have these long wavelengths, averaging over 15,000 meters.
Wow.
While the secondary channels are much shorter, around 3,700 or 3,800 meters on average.
Okay.
And what's really insightful here, something the study emphasizes, is that the islands themselves, their presence, their dynamics, are what give the main channel the sort of pseudo-meandering behavior.
Real meandering.
Yeah, they constantly influence its curve and direction, but without it forming those classic high-amplitude meander loops that you'd see elsewhere. The islands kind of guide and shape the flow.
So the islands are really active participants, not just passive obstacles.
Absolutely. The river's shifting hearts, as you put it earlier.
Let's talk more about those islands. What did the research find about how they interact with the flow splitting and rejoining?
They looked at the angles. The bifurcation angles where the flow splits to go around an island are generally larger, and they correlate more strongly with the size of the island than the confluence angles where the flow rejoins downstream.
Interesting. So the split is more directly related to the island size.
It seems so, and there's this really strong correlation, almost perfect, between the number of islands in a structure and the number of secondary channels. The correlation coefficient was 0.955.
That is incredibly strong. More islands mean more secondary channels, basically.
Yes. And here's something quite specific to the Amazon that the study highlighted. The Peruvian Amazon actually has more secondary channels compared to anabranching rivers that have been studied in other places, like parts of the U.S. Midwest.
Really? Why would that be?
Well, that's a great question the research raises. What are the unique factors in the Amazon, the sheer scale, the sediment load, maybe the bank material, that contribute to this higher density of channels and islands? It points to a specific set of local conditions fostering this incredibly complex, multi-thread environment.
Okay, that's the static picture. Let's shift now to the dynamic dance.
Yeah.
The erosion, the deposition, the migration. What patterns did they see over those 35 years of change?
They found these cyclical and successive trends in erosion and deposition. Overall, there was a slight prevalence towards deposition, slightly more land being built than eroded over the whole period.
Okay, a net building effect, but with cycles.
Right. And crucially, looking at these patterns through the lens of the island structures How the islands themselves form, grow, shrink, disappear gave a much more nuanced picture of how the river adjusts. It's not just about bank erosion here and deposition there, it's about the whole structure evolving.
Were there specific hotspots, areas where things were changing much faster?
Absolutely. The highest rates of deposition and overall activity were seen right near the beginning of the study reach, near that confluence of the Marañón and Ucayali rivers where the Amazon proper starts.
So a very dynamic starting zone.
Highly dynamic. Conversely, they found significant peaks in erosion downstream of where major tributaries join the main Amazon.
Oh, like the Napo.
Exactly.
Yeah.
The Napo, the Cachiquina, Ataquari, Yavari rivers, where they dump their water and sediment into the main stem, you see increased erosion just downstream.
Suggesting those tributaries kind of stir things up locally.
It strongly suggests a direct link, yeah. Like a local disturbance that forces the main river to readjust right there.
And the main channel itself, it's constantly moving sideways, right?
Yeah.
Sometimes quite dramatically.
Oh, yes. The lateral migration rates, how fast the channel shifts side to side, show these large oscillations over time. And the biggest peaks in migration speed were found in those compound or unstable structures they identified.
Like which ones?
Structures like 1B, 3A, 5, 10A, and 17B showed particularly high migration rates. And to give you a really concrete example of this dynamism,
Yeah.
structure 5, it showed significant development early in the study period. But by 2020, it had essentially disappeared entirely as a distinct anabranching feature.
Wow, an entire structure just vanished, absorbed back into the river.
Basically, yes, it highlights the river's incredible power to completely reorganize itself over just a few decades.
That's truly mind-boggling. So what was the average speed of this constant shifting for the structures overall?
The average speed at which the centers of these anabranching structures moved their centroids was about 79 meters per year.
79 meters.
Right.
That's significant movement year after year.
It is, or almost 100 meters per year if you include some outliers. And importantly, this speed is directly correlated with that activity metric we talked about, the erosion and deposition within the island structures.
So more active islands mean faster movement of the whole feature.
Exactly. More dynamic islands lead to faster overall displacement and the predominant direction of this movement, generally southeast.
Okay, so the river is constantly moving, constantly reshaping. But are there underlying patterns to where these structures form? Did the researchers find any rhythm or periodicity?
Yes, and this was a really key finding. There's a surprising spatial periodicity. These anabranching structures don't just pop up randomly.
No.
They occur on average about every 22.4 kilometers along the stretch of the Peruvian Amazon.
22 kilometers. Is there a way to relate that to the river size?
Yeah, that translates to roughly every 15 channel widths.
Every 15 channel widths, a new anabranching structure tends to form. That suggests something regular is going on.
It really does. It hints at some kind of underlying geological control or maybe a large-scale hydrological rhythm that dictates where these massive features develop. It's not chaotic. There's a hidden pulse.
A hidden pulse. I like that. And you mentioned the river's origin earlier, the confluence. Does that starting point play a special role in setting up this dynamic?
It absolutely seems to. The confluence where the meandering Ucayali meets the anabranching Marañón, the inlet region, creates this inherently unstable, highly dynamic environment right at the start.
Okay.
The researchers describe it as a kind of transitional adjustment zone. It seems to absorb a lot of the initial morphological energy, lots of change happens there, and that sets the stage, influences the development of all the subsequent anabranching structures downstream.
Like a ripple effect starting from the confluence.
Something like that, yeah. It's like a natural control point that influences everything that follows.
Okay, that makes sense for the origin. But you also mentioned stable versus unstable structures. The Amazon seems to prefer forming single, stable ones generally. So why do some become compound or unstable? What pushes them over the edge?
That's a crucial question, and the research points pretty directly towards the influence of those significant tributaries we talked about earlier.
But the Napo, Yavari, etc.
Exactly. When a major tributary flows into the main river, its added discharge, the extra water, and its own sediment load can apparently be enough to convert a previously stable structure into an unstable one.
Yeah.
It seems to increase the number of secondary channels and islands, making the whole thing more complex and prone to rapid change.
So there's a tipping point.
It strongly suggests there's a geomorphic threshold for tributary influence, a certain amount of added flow or sediment that tips the balance. Pinpointing exactly what that threshold is, that's a key area for future research.
And beyond the water and sediment flowing in the river, does the surrounding landscape the valley itself play a role in guiding how the river behaves?
Oh, definitely. The underlying geology of the Amazon Valley and its floodplain acts as a sort of guiding hand.
How so?
The river channel often bumps up against or abuts the edges of the valley. The left and right margins, which are typically older, more resistant terrain.
So it can't just wander anywhere it wants.
Exactly. This physical confinement limits its lateral movement. And that, in turn, profoundly influences both the spacing, that periodicity we discussed, and the orientation of the anabranching structures. The valley shapes where and how they can form.
Okay, so we have the river's internal dynamics, the tributaries stirring things up, and the valley providing the outer boundaries. It's a complex interplay.
It really is.
So let's pull back to the bigger picture. What does this all mean for us and for the future of the Amazon? This deep dive reveals a really unique kind of river equilibrium, doesn't it?
It does, unlike the classic meandering rivers you learn about, which rely on those dramatic cutoff events to sort of reset and maintain balance. These anabranching rivers achieve their morphodynamic balance differently. They do it by oscillating, by adjusting the number and size of their secondary channels and islands over time.
A constant, gentler adjustment rather than sudden shifts.
In a way, yes. And this dynamic balance creates an incredibly complex, diverse, and importantly, resilient habitat, a very rich biotope.
Which makes them desirable for restoration projects elsewhere.
Exactly. River managers are increasingly looking at anabranching patterns as models for restoring degraded river systems because they offer this combination of stability and a habitat diversity.
But the stakes seem particularly high for the Amazon itself, given everything happening there.
They are incredibly high, and this study points out something critical. Deforestation across the wider Amazon basin is already changing sediment concentrations in the rivers.
More sediment washing in, or less.
It can be complex, but changes in land cover definitely alter runoff and erosion patterns. And those changes have potential knock-on effects on the river's ecological functioning, on freshwater availability, and on the river's shape itself, its geomorphology.
And it's not just deforestation, is it? The study mentioned potential human interventions in the river.
Yes, and this is where this kind of baseline understanding becomes so vital. There's a significant knowledge gap regarding proposed mega projects.
Like what?
Like the Peruvian Amazon Waterway Project, the PAW, which involves extensive dredging to deepen navigation channels, and also various proposals for hydropower dams along the main stem or major tributaries.
Dredging and dams sound like they could fundamentally alter the system we've just described.
They absolutely could. They could significantly disrupt the natural equilibrium of these anabranching rivers, the very way they transport sediment and adjust their form. This deep dive, this research, effectively serves as a crucial baseline study.
A snapshot of the river's natural state.
Exactly. It helps us understand the river's incredibly complex natural behavior before these potentially massive human interventions take place.
So wrapping this up, what does this all mean for you listening? The Amazon, particularly this Peruvian stretch, isn't just a static line on a map. It's this constantly shifting anabranching masterpiece. It maintains its balance through this intricate dynamic dance of channels and islands. It pulses with that surprising periodicity roughly every 22 kilometers.
That rhythm, yeah.
And its stability, or instability, is profoundly influenced by those powerful tributaries feeding into it, and by the geological constraints of the ancient valley it flows through.
It's a system shaped by both internal processes and external forces.
So here's the final thought. Considering this river's incredible natural dynamism, its inherent ability to adjust and maintain itself, and its critical role in nurturing some of the richest biodiversity on Earth, what responsibility do we have when we propose large-scale human interventions, things like extensive dredging or building new dams?
It's a huge question.
If the river naturally achieves its balance by oscillating, by constantly adjusting its channels and islands, how might our attempts to control it, to fix it in place, or drastically alter its flow and sediment, inadvertently disrupt the very processes that make it so resilient and unique?
Could we be undermining the very things that allow it to function?
It's something to think about. This knowledge, this deep dive into the river's pulse, provides a really powerful lens through which to view any future development in one of the world's most vital and most dynamic ecosystems.